Hi everyone, we are now starting. What we're doing today, you guys won't know tomorrow. I mean, at least in theory, because this is going to be the shortcut for how to find integrals. And I'm going to caution you back that though you're going to know this technique, you still need to know the theory behind everything that kind of leads up to the first half of this chapter. Also, the fundamental theorem of calculus has two parts. This is just focused on the first part. The second part can be the more confusing of the two, and yet is the more important of the two. So if I had to go with what part one really defines, what it really defines is the definite integral. And part one is focused on the definite integral. And the definite integral, as we did over the last couple of days, represents the area between a curve and the x-axis. Area appearing above is positive, area appearing below is negative. And the way that this goes is if f is continuous on a to b, and big F is an antiderivative of little f on a to b, then the integral from a to b of little f of x dx equals big F of b minus big F of a. Now, something that many of you who have seen this before will not immediately be aware of, and this is going to be a little sidebar here, is what I'm going to call over the next year plus the most important formula in all of calculus, and I don't say that lightly. This is not going to be the thing where I say that about many things. I will say that about this. This is the most important formula in all of calculus. Because if I change the relationship here to here to here to actually be this, the integral from a to b of f prime of x dx is equal to f of b minus f of a. And if I actually solve for one of those, f of b equals f of a plus the integral from a to b of f prime of x dx. This is the formula that I am calling the most important formula in all of calculus. There will be about 3 to 5 questions on your AP exam alone that deal with that formula. That can be the difference between a 4 and a 5. And that formula and its applications will be repeated continuously over the year. This is not an obvious formula, although you see where it came from in the derivation from the first fundamental theorem to where it occurs. Oftentimes you're given a first derivative or a graph or a function of the first derivative, and you're given one value that may not be f of 0, it might be f of another point. And you're asked to find f of another point. This is how you do it. The integration can be done manually. It can be done by graphical analysis. It can be done by areas. How it gives you this may be not obvious, but the formula itself leads you to the solution. So I'm going to call this is the first time I'm introducing it. I usually wait a couple weeks to tell you this about this most important formula, but right now I do want you to see where it comes from and how we get to that, even though we're going to kind of swing back to this formula and talk about this for a second. So very, very rarely you guys are now going to ever do areas directly. You may, and I want to caution you, the semicircle one, finding the area, is still the only way that you guys will have to calculate the area of the semicircle. That's not going to be done manually. That will be done by recognizing that it's a semicircle. But how this works is about as easy as can be. We take the integrand, a word that means the thing you're taking the integral of, or I should say a word that means the thing of which you are taking the integral. See what I did there? We integrate x cubed minus 1 to x to the 4th over 4 minus x. And the notation I'm going to use is that this what I call an antiderivative is going to be evaluated from 2 to 3. That notation I want to see. I don't want you to jump right away to the substitutions, because now we're just going to plug 3 in, 3 to the 4th over 4 minus 3, and subtract what we get when we plug 2 in. 2 to the 4th over 4 minus 2. There's no c. There would be if I took an antiderivative, but the c's would cancel. You'd have a c minus a c. We don't include c's when we have definite integral. Your result in a definite integral is a number. And that number here, 81/4 minus 3, minus 2 to the 4th over 4 is 4, then plus 2. 81/4 minus 7 plus 2, and 81/4, sorry, it should be 81, not 84, 81/4 minus 20/4, or 61/4. Please express all results of this using improper fractions, even if I'm allowed you to use a calculator. I should have clarified that, and I will next year, and I did for these guys on the last quiz, that if you guys are calculating LRAM, MRAM, RRAM, and TRAP with a calculator's assistance, I still want them as improper fractions, especially because I have to be the one to grade them. Okay, next one. Number 2. The integral from -5 to 0 of radical 25 minus x squared dx. We are going to use all of our techniques that we have, and the technique here is one of, we are going to recognize exactly what kind that is. I told you guys that we will not be using U substitutions or any other substitution methods for a semicircle. This is just a semicircle centered at 0, 0, and I'm asking for the area of this thing. 1/4 of a pi r squared. 1/4 pi times 5 squared, or 25 pi over 4. I'm going to do a little sidebar here too, because this is, again, now less me about obsessing over tau and more me about teaching you guys the proper way to find the area of a circle so that you can modify that if you want the area of a sector or a part of a circle. This is elevated to become just less of a curiosity and more of a way to remember what my BC kids needed to do. And I told you last week that they messed up an AP problem because they didn't know this. You guys at times have all done 1/2 mv squared, 1/2 at squared. God, what's another one? There are more. There's one I'm forgetting. What? Well, mv is momentum, but the momentum is the integral of momentum is, why am I forgetting this? Is that a force due to gravity? In any case, 1/2 something something squared is a constant in mathematics. And 1/2 tau r squared, where tau is 2 pi, is the area of a circle. And if I change that to be the area of a sector, I now change the tau, which was 1 trip around the circle in radians, to be just any angle. 1/2 theta r squared is the area of a sector. So you guys should keep that in your brains, and hopefully, at least if you have me next year, we'll keep reiterating that whenever we bring up tau, so that when we get to this, that will be something that's very second nature. At least tell me you guys realize that if you learn it from tau, then finding the area of a sector would have never been a big deal. You would never have to think in terms of dividing it by 360 or dividing it by, or taking it out of there. You would always just know intuitively what the area of the sector is. And now it has this massive disconnection with the area of the circle because, let's just face it, we suck. Okay, back to this. Let's go to one that you guys now can do. The integral from 0 to pi over 2 of sine of x dx. If you're at least somewhat into the mathematical curios, you may find this a little bit interesting to figure out what each one of these is. So let's grid out what area we're actually talking about. I'm going from here to here to here, and I want to find what the integral of basically half of the hump is. I'm going to let you guys do that while I pause it for a second. Okay, back to this. What'd you find? It is 1. The antiderivative of sine is negative cosine of x from 0 to pi over 2. I do want to talk for a second about the constant multiplier because the negative in front of the cosine can be factored out. So you're just doing the negative of the cosine of pi over 2 minus the cosine of 0. That can be easier in the head to think about. Cosine of pi over 2 is 0. Cosine of 0 is 1, and you have negative negative 1, which is 1. If I was obsessed with tau, there are some people who are obsessed with 1/4 of a tau. Thank you. Okay. Anyway, 1/4 tau is called eta. By those that like that, when I said draw each eta back when we graphed these things, do you remember? Kind of remember that? So there's this whole operation that like it should also be etas, and you should be thinking about like one trip around the circle is 4 quarters, and every quadrant gets its own special thing. But you guys should now kind of synonymize that. That it's not just that the areas cancel; it's that the areas are 1, 1, negative 1, negative 1 for all of that. So just kind of keeping that in mind. The same is true for cosine until you start shifting, and then it gets messed up. Okay, number 4. I'm going to leave this on you guys. The integral from 1 to 9 of 5 root x dx. As we've done before with constant multipliers, pull the 5 out, and at least in your head, if not on paper, rewrite this as x to the 1/2 dx, so that you're not pulling your brain power too much. Another trick is that when you raise the 1/2 to a 3/2 and then multiply by the requisite 2/3, multiply the 5 by the 2/3 and keep that factored out as a 10/3. So really you have 10/3 times x to the 3/2 from 1 to 9. This is also why we spent so much time in Algebra 2 on rational exponents. This should be second nature by now. 10/3 times 9 to the 3/2 minus 1 to the 3/2. I had a senior last week ask me how they could do that without a calculator because they're trying to do 9 to the 3rd power. Well, not only would I expect you to know that 9 to the 3rd power is 729, I would rather you do what? Yeah, take some square root it first. Square root, then raise 27 minus 1, and you get 260 over 3. So I'm not going to spend the whole period doing just examples of this. This is easy. Let's get to some of the more examples that are going to be more tricky, like this. The integral from 0 to 3 of the absolute value of 2x minus 3 dx. How to analytically take an absolute value integral. You guys should know that one strategy you have is to split the integral across the cusp and to graph it on graph paper and figure out what the integral would be. But if you don't know that and you don't want to graph it on graph paper, let's at the very least graph it in your heads. Where does the cusp occur? 3/2. So it's going to look something like this, integral from 0 to 3, but you just need to know that this is going to be a piecewise. And so how to take an absolute value and split it to a piecewise means that if I have y equals 2x minus 3, that means that y is equal to, well, to the right of x, or 3/2, it's going to be exactly the same. X is greater than or equal to 3/2. And to the left of 3/2, it's going to switch sign. Negative 2x plus 3 when x is less than 3/2. This is also a concept that reviews what we did, believe it or not, back in September of your freshman year. Taking an absolute value and splitting it. Every absolute value we did then was linear. You guys actually should now be able to do that with nonlinear absolute values, because the cusps are going to occur, the branch points are going to occur anytime the graph crosses the x-axis. So you should be able to find zeros and split them across wherever it's happening, making negative anything that pops below the x-axis. So the integral is going to look like this. The integral from 0 to 3/2 of the positive one. Nope, kidding, the negative one, because the negative one's the one from 0 to 3/2. Plus the integral from 3/2 to 3 of the positive one. So how this kind of works now, I can factor the negative out and make it the negative integral from 0 to 3/2 of 2x minus 3 dx plus the integral from 3/2 to 3 of 2x minus 3 dx. Now we can integrate. The integral of 2x is x squared. The integral of 3 is 3x, evaluated from 0 to 3 halves, plus x squared minus 3x, evaluated from 3 halves to 3. Let's get the same wording going on there. If I am saying evaluated from, I evaluate from lower limit to upper limit. Sometimes people mess up the order when they're saying it because the upper limit's on top and they're reading it that way. That's just not how it's done. So we have negative 3 halves squared minus 3 times 3 halves is 9 halves. This is going to be minus 0, even with the negative out in front. Then plus 3 squared minus 9 minus, parentheses, 3 halves squared minus 9 halves. Need a plus there, right? If I don't put parentheses and kind of overuse them in places, I'm going to kind of run a gamut of messing signs up. That's correct. So I get negative 9/4 minus 9 halves plus, actually in this case, minus 9/4 minus 9 halves. 9/4 minus 9 halves is negative 9/4. 2 negative 9/4 is going to be, or 2 negative 9/4. Should this whole thing be 9 halves? I'll let you math that out. Okay. Number 6. The integral from 0 to 8 of x minus 4 cubed dx. Let's just do another one. Plus the integral from 0 to 8 of 7 dx. I kind of want to teach you the first one right now, even though that's coming a little bit later with U substitution. But you guys are in honors AP class, so you can handle it. The way that you would want to do it without knowing U substitution is to expand x minus 4 to the third, and then do it each part. But we can do better than that. I'm going to treat this one separately for a second, because the best thing to do is to take that x minus 4 and let that be equal to a u. I love U substitution when you do definite integrals. Love it, and you will too, because it makes the problem easier. Here's how. Even though du is just dx, the thing that you're going to have to remember is that your limits of integration, the 0 and the 8, are both x values. So not everything has been converted to u's yet, but we could convert those to u's. We have a function that takes x and changes it to u. This one. So what you're going to do is you're going to do a 3-part substitution. You substitute your limits by taking your limits and plugging them in to the function for u. You take your limits of 0 and 8 and you plug them in. In fact, I want to show this just this once, that u of 0 is equal to 0 minus 4, or negative 4, and u of 8 is equal to 8 minus 4, or 4. And your integration now becomes the integral from negative 4 to 4. It's no longer x minus 4. It's u cubed. It's no longer dx. It's du. And that integral happens separate from the other one. Heck, I can go ahead and just integrate this 7 and get 7x evaluated from 0 to 8 and finish that part out. But this right here never has to return to x's ever again. You've taken a more complicated integral and made it a simpler integral. And the better part of this is that you should already know, pun intended there, you should already know, what what that integral is. Why?
It's one of those places.
Yeah. We're going to evaluate this manually because chances are in a couple of months you're not going to be thinking about even odd functions. But this is just the integral of u cubed, which is that, and it's perfectly symmetrical about left to right. I'm going from -4 to 4. Shouldn't my negative area perfectly cancel my positive area? And that integral equals 0. Let's prove it. U to the 4th over 4 evaluated from -4 to 4. 4 to the 4th is the same as 2 squared to the 4th, or 2 to the 8th, which is 256. 256 divided by 4 is 128/64. Or let's just pull out the 1/4 and just do 256 minus 256. But yes, this becomes 0. This right here becomes plus 56. So if I carry that down, this whole integral becomes 56. And that is the fundamental theorem, part 1. Okay. Questions on that so far? Yes?
On the very important equation you said on the front side.
Yes, the most important.
Why did you rearrange? Well, why is it the first way you wrote it the way you keep it? Why did you rearrange it right?
Well, the first way I wrote it represents how we evaluate definite integrals.
No, about the one below that.
One below that? Because when this important thing is used, when when this happens is when you're trying to find f of a number. So what may happen, let me just kind of throw it down here at the end, just to show you an example of this. You may get a problem that at its very simplistic sense says this. F prime of x is equal to 3x squared minus 1. F of 2 is 4. Find f of 1. Now, that's not obvious that you would know what that is. It's really not. But if you know that most important formula, you could say f of 1 equals f of 2 plus the integral from 2 to 1 of f prime of t dt. Now, later about why I'm using t's and not x's here. It doesn't really matter that I'm using t's and not x's. I'm just doing that so I don't have the same variable mean different things. But I can now actually evaluate this. F of 2 is 4. F prime of t integral is x cubed minus x, and evaluated from 2 to 1. Even though it's negative, that's not a big deal. I get 4 plus 1 cubed minus 1 minus 2 cubed minus 2. 4 minus 6. I know that f of 1 is -2. I was able to find f of another number by just knowing what 1 point was and what the derivative was. That will be the power of it.
But didn't we also evaluate that by taking the integral of the derivative and then finding the c value?
We did. This bypasses that whole thing. This saves some brain power and a lot of like simplistic things. And plus, if you don't have this in your brains, what about when the integral is done by an area under the curve? So I'm not thinking c value then. Like maybe it's a graph of f prime it's giving me, and the integral of the graph is the area under the curve. Or maybe it's a table of values they give me, and so it's kind of all this. It can be tricky about how this comes up. Yes, finding the c value is the long manual way to go about it. Okay, your homework for this that's going to be due the next time we meet after the test, which I think is Wednesday, is if you guys could write this down so that I don't have to refer to this in the middle of the test and have someone write it up on the board, although I'll probably do that anyway. That's due on Wednesday, and I'm going to stop recording here.